Alright. So, okay. Yep, seems about right. So, I'm on the record ranting and raving that Pallavi ma'am's explanations of whatever she's been explaining of late are complete and utter incomprehensible bullshit. It is possible I'm just being a cynical asshat, but on the off chance I'm not, I'm gonna try to put my money where my mouth is and see if I can explain the stuff better. So I'm going to start by explaining a bunch of things that I feel like she should have explained before ever even daring to begin what she explained today. So, the first thing that I'll start to explain to you all will be the concept of distributions, and I'll focus on normal distributions because that's what's relevant to us. Then from there I'll go to the idea of samples and IID samples, and then hopefully if my belief is right, and my belief, for those who don't know, is that ma'am has essentially started, so anything you're explaining has a beginning, a middle and an end. My belief is that ma'am has started halfway in the middle, and as a result any understanding that follows from her is either it's either wrong or non-existent because someone couldn't understand it, or it's incomplete. And so theoretically I'll be able to start from not quite the beginning, because to start from the beginning would take way too long, but I'll be able to start from closer to the beginning than where ma'am started, and as a result you people will understand it. It'll be more comprehensible, and in the process I'll understand it better too, because to be frank, I did this stuff quite a while ago and I don't remember it perfectly myself. So we'll start with the idea of data distributions. So any data has a domain that it takes. So simple example, coin toss, right? It's got a domain consisting of two values, zeros and 1. 0, 1. Okay? And it takes, so within its domain, it follows a uniform distribution. That is to say, the probability that it takes a 0 is equal to the probability that it takes a 1. That's a uniform distribution. Fair enough. Likewise, the normal distribution. So the normal distribution, okay, I'll pick an example of a normal distribution. The height of humans. I'm pretty sure that's a normal distribution. So the range of a normal distribution is anything from minus infinity to plus infinity. Okay? That's the technical range. But the probability that it takes any value along that range is governed by two variables, the mean and the variance. So taking the heights of humans, for example, the mean would be around 6 feet, I'm assuming. I'm not sure. And the variance, again, I've not looked this up, I'm not doing it technically, I'm just using intuition. The variance would probably be, I don't know. The variance would be some amount of inches, right? Because you don't have it's not like the average is 6 feet humans, but you also very often find 4 feet humans. They exist, but they're rare. And so the variance is in inches. And so if you were to graph that, the x-axis is, so this is minus infinity, this is plus infinity. Apologies if my handwriting is even shittier than usual. I'm writing this off at an angle so that you guys can see it. This is minus infinity, this is plus infinity. Somewhere along here will be 6 feet, right? And if I go around measuring human beings and I compute the probability, so this is, let's say this is 6 feet, this is 5 foot 5 inches, this is 6 foot 5 inches, right? These are all values. And I go around trying to find So I go around taking a bunch of people and I pinpoint what their heights are. Okay? What I'll find is that and this is the number of, the y-axis has the number of people whose heights are this particular value. I'll find the overwhelming number of people will be 6 feet. There'll be some who are 5'8", some who are 5'7", and so on and so forth. And as we go down in terms of, so as the height decreases, the number of people who are at that height decrease. So when you say the heights of people follow a normal distribution, what you are saying, when you say that the heights of people follow a normal distribution with a mean of 6 feet and a standard deviation of roughly 5 inches, what you are saying is that the probability of a person's height being the highest, God, let me phrase this properly. The highest, a person is most likely to be 6 feet high, and on either side of that, less than 6 feet, more than 6 feet, the probability of their height taking a value decreases. That's what you're saying when something follows a normal distribution. Comprendia? Alright. Now talking about samples and IID samples. Now I kind of illustrated this implicitly when I was talking about the heights of people. But IID samples, what is that? It means identical independently distributed samples. Okay? So there's 60 people in our class, right? I ask for the height of Yash. I get his height. Let's say his height is whatever the hell it is. I'm gonna assume it's 5'11", something like that, right? Now, my knowledge that his height, this goes back to this goes back to independence as per probability and statistics in the previous term. My knowledge that his height is 5'11" has zero bearing on my estimation of what Jehan's height will be, right? So that means independent. It also means identical, because Yash's height and Jehan's height and my height and Anushka's height and Hitar's height and so on and so forth all follow the exact same distribution, which is the distribution followed by the heights of human beings, right? So identical independently distributed samples. Okay? So now where this links up with normal distributions, which is what she's been talking about. You can use this test when your data is normal. What the fuck does that mean? Okay? What it means is there's this rule, this idea, and this part I'm not sure if I should explain it or if you can just kind of get by without it, but I'm gonna. The idea is, so you can take n samples of a particular thing. So I can measure the heights of n people. I can toss a coin n number of times, right? As you start taking n samples, as n tends to infinity, regardless of the original distribution, your data starts to follow a normal distribution. Now what the fuck does that mean? Okay, say I have a coin toss, okay? And I toss the coin 10 times. So I'm probably gonna get head, tail, right? Something like that. Now I toss it 100 times. I'm probably gonna get 52 heads and 48 tails, something like that. Now I toss it 1,000 times. How the hell do I phrase this? Okay, yeah, I've got it. Now I toss it 1,000 times. And now my variable that I'm considering is the number of heads in 1,000 coin tosses. It will follow a normal distribution. So I already mentioned that the individual coin toss follows a uniform distribution, but 1,000, okay, yeah, you guys really do not need to know this, and I understand to some degree why man skipped it, but no matter. 1,000 coin tosses, right? The mean, the x-axis here has number of heads, the y-axis has probability of that number. So I toss 1,000 coins. The highest probability is of 500 heads. This is the probability of 490 heads. This is the probability of 510 heads. This is the probability of 450 heads. This is the probability of 550 heads. This is the probability of 300 heads. And so on and so forth. It ends up following a normal distribution. That much we're clear. Now that I've kind of given you sort of a basic general background, we can move on to hypothesis testing. So, I put forward a hypothesis that okay, so, alright, as I've kind of noted throughout, it's possible I've been being overly cynical. It's also possible I've been underestimating your guys' intellect. If so, I would apologize, except that's just what I do, so no matter. Anyways, so maybe I'm just explaining the obvious, maybe not. Or maybe I'm just going through the basics to make sure that they are concrete before I go further. We'll see. Anyways. What am I doing now? Can you tell I'm not prepared at all? I'm just doing this off the cuff. Anyways, okay. So my hypothesis, okay, now we can move on to hypothesis testing. I'll cover sort of what man has been trying to say with hypothesis testing, and then I'll cover the specific things that, okay, so hypothesis testing, null hypothesis, alternate hypothesis. She's more or less said this, but I feel like she could have said it way more concretely and way more specifically and pointedly. And Sagarika actually, today when we were chatting, she said it way better when she was explaining it to Jehan. Your null hypothesis is effectively that nothing has changed. That, as far as I can recall, that's not how I understood it. But Sagarika said that today, and that makes way more sense. So, generally your hypotheses will be of the form of, this used to be the state of things. Now we believe it has changed. Has it or has it not? So, to not take the same examples again, you have a machine. It used to have a mean failure of machine's meant to do something. It fails to do that on average 10 times. 10 times. It on average fails to do that 10% of the time. What we suspect is that probability has increased just due to wear and tear, and it now fails to do its job 15% of the time. So the probability of it failing to do its job is 0.15. Our null hypothesis is that the probability that it fails to do its job is still 0.10. And the alternate hypothesis is that the probability that it successfully does its job is 0.15. I think this part Nam probably ended up covering reasonably well. I'm honestly not sure because I haven't been paying attention to it because I've been too busy screaming inside my head. what I'm pretty sure she did not cover well is significance level. So significance level is reasonably simple, and let me check that I've got it right because I forgot. Pretty sure I've remembered correctly, but need to double check. Where the fuck is it? Right. Yep, I've got it right. So, your significance level in any sort of situation is the probability that you reject the null hypothesis while that hypothesis is true. So what do I mean by that? It is the probability that we say, okay, yes, the significance level is the probability that we say that on average, yes, this machine does fail more often now, when in fact it still fails only 10% of the time. That's the significance level. And I have no idea. So confidence level is a new concept to me, but confidence level, as far as she's calling it, is just 1 minus significance level, which interpreting that, significance level is equal to probability reject H log null hypothesis given H log is true, right? So 1 minus significance level will be probability that you accept the null hypothesis when it is true. Fair enough? Now, how does this, so now let's take this, so this problem of machines, is the machine still failing 0.10 or 0.15% of the, 10 or 15% of the time? Let's look at how you'd actually do that. How you'd actually check that. Apologies. You would have the machine do its job 100,000, 10,000 times. Let's go with 100 just for my ease. Okay? And you'd see how many times does it fail. Let's say it fails 12 times. That's the number of failures. Right? So that's telling you that so if you were to just go based on that, you would say there is a 0.12 possibility of failure. But that's not how we do things here. 0.12 is this particular sampling. So here's what I mean. Okay, this I should have introduced earlier. Sampling versus sample. I have the machine do its thing 100 times. Once, I get 12 failures. The next 100 times it does its thing, it may fail 13 times. The next 100 times it does its thing, it may fail 14 times. I apologize for the drill sound, there's construction going on outside. Right? And so, what this tells you, that when I ran the machine 100 times, it failed 12 times, it's only giving me information about this specific sampling. It's not giving me information about the machine as a whole. And so, what you need to do, sort of, is convert this and make it information that's telling you about the machine as a whole. So how do you do that? So, the machine's failures follow a normal distribution, right? So it follows the normal distribution with mean equal to something and variance equal to something. For the time being, I'm going to assume variance is equal to 10, right? I'm just making my life easy. Now mean, what's the mean? If the null hypothesis is true, then the mean amount of failures is, mean probability of failures, the mean amount, is 0.10. If the null hypothesis is false, then the mean amount is 0.15. So as of present, we do not know what the actual mean is. Mu equal to unknown, sigma square equal to 10. Okay? Or let's go with 4 actually. The variance in terms of the number of times this machine fails is 4. Now when you're computing significance level is the probability that you reject the null hypothesis given that the null hypothesis is true. So while you are computing the significance level, you are going to assume that the actual number of times the machine fails follows a distribution MF, machine failures, not motherfucker. MF follows normal, mu equal to 0.10, sigma square equal to 2. You're going to assume that because you are computing significance level specifically, which is the probability that you reject the null hypothesis, which the null hypothesis is mu equal to 0.10, given that this mu is actually equal to 0.10. So when would you reject this null hypothesis? Let me grab a different sheet of paper. When do you reject this null hypothesis? This is where we come to what she's been talking about in terms of acceptance regions, which all she's done is just name drop it. Like acceptance, this you can see is an outside the acceptance region. This you can see is a left-tailed, right-tailed test without ever explaining what the fucking acceptance region is. I need to drink water. So now, let me explain to you what an acceptance region is with this same example. So, I'm gonna assume that my distribution has a mean of 10 and a standard deviation of 4. Okay? So now I do my test where I run the machine 100 times and I get 12 failures. Is that a success or a failure? Has the probability of failure increased to 0.15 or is it still 0.10? So now that fundamentally there's no mathematical way to tell that, but what you can do is choose that. So you can decide, okay, when I run my test of running this machine 100 times, when I get that sample, if the sample mean is greater than 13, I'm gonna assume that the probability of failure has in fact increased to 15. 2.15 to 15%, right? So that's what you're doing, and that is linked with the significance level. So they fix the significance level as 0.05. Usually whenever you do any sum at our level, and even at the level at which I was doing this, which was, I'm gonna hazard a guess, it'll probably be slightly more advanced than what ma'am expects, or just slightly more thorough, I'd say, not advanced. You'll usually get a significance level of 0.05. Okay? And so what does that mean? That means the probability that you reject the null hypothesis, given that it is true, is 0.05. What does that mean? So here my null hypothesis is that the probability of failure is 0.10. My alternative is that it is 0.5. If I decide that at 0.13 I'm going to exceed at that for a sample mean failure of 0.13, I'm gonna determine that the null hypothesis is false, and the significance level is 0.05. You guys may need to rewatch this because I can't keep on going back to what I've already said. So you may need to rewatch it just to follow my train of thought. What this means effectively, if I fix my failure point as 0.013 at 0.05, what that means is that if I do a test of where I run the machine 100 times, I get greater than 13 failures. There is a 0.05% chance that I get greater than 13 failures even when the actual real probability of the machine failing is still 0.10. Because that's the thing you need to understand. The sample mean is not the same as the distribution mean. Every time I run a test of running this machine 100 times, I will get a different sample mean for number of failures. Sometimes it will be 0.12, sometimes it will be 0.13, sometimes it will be 0.14. Sometimes it will be 0.8, sometimes it will be 0.7, sometimes it will be 0.6. That can happen, and the actual machine failure rate can still, the real true machine failure rate at the distribution can still be 0.10. But you are using a sample to conclude if the actual distribution mean has changed. You get what I'm saying? And so you're kind of guessing, okay, I got a sample which is this high. Is that just a really weird sample, or is that indicative of the fact that the distribution mean has changed? Right? And so what you are doing there, so that's what you're computing. Okay, so now, okay, I'm gonna explain all of this again, but hopefully something in what, not all, because I suspect that from what I've been talking to y'all, some parts may have made sense, some parts y'all haven't been following along, but now even I'm more concrete in terms of what I'm getting at, what I need to say, so I'm gonna explain parts of it again. So, acceptance region. That is something you define where for this, okay, what's the time? Alright, we're 27 minutes in, my god. Alright. Sample mean, I'm just listing down what topics I need to cover in a systematic manner. Distribution mean, right? Acceptance region, tails. Okay, this is what I need to cover. So I'm gonna cover all of this again. Alright? Sample mean and distribution mean. So I'm gonna go to the most basic bloody example. Coin toss. A fair coin, which hopefully this is fair. Hopefully I didn't use this to cheat at gambling. A fair coin follows a uniform distribution where the mean will be 0.5. Let's say I toss this coin 10 times. I could get 6 heads. That gives me a uniform, that gives me a sample mean of 0.6. Let's say I toss it 10 times again. Suddenly I get 4 heads. That gives me a sample mean of 0.4. And so on, so forth, etc., etc. And what you are doing in any real world situation is you are taking a sample and you are estimating the real world distribution from that sample. And you are trying to infer the real world distribution from the sample. Okay? So, you've done that. So now, I've already said what null and alternate hypotheses are. So now, acceptance regions. So let's drop that machine example. Let's go with the simplest one, a coin toss. I want my null hypothesis, HO, is that probability of heads is 0.5. This is in effect saying that my null hypothesis is that this is a fair coin. Now what could be my alternate hypothesis? There's a couple. There's a few alternate hypotheses. My probability of heads is less than 0.5. My probability of heads is greater than 0.5, or just simply my probability of heads is not equal to 0.5. These are all All of these are just ways of saying that the coin, my alternate hypothesis is that the coin is not fair, but they have implications upon the tails, two tail test or left tail test, right tail test, or acceptance regions. Okay? So now, I'm finding significance level. I know that when I take 1,000 coin tosses, they follow a normal distribution, or with a when you're computing significance test, as I said earlier, we assume that the null hypothesis is true. So if the null hypothesis is true, if the probability of heads is 0.5, then I know that if I'm tossing this coin 1,000 times, the mean of that the mean number of heads is 500. Okay? And as I explained earlier, just by way of infinite number of identical independently distributed samples, the number of heads, that variable, the number of heads out of 1,000 follows a normal distribution. So now, acceptance region. When I say that, so okay, if my alternate hypothesis is that this is an unfair coin because the probability of heads is in fact less than 0.5, I'll define an acceptance region of 495. What's that saying? If I toss this coin 1,000 times and I get less than 495 heads, I am rejecting the null hypothesis. If I toss this 1,000 times and I get 497 heads, I am accepting the null hypothesis. And if you look, my acceptance, to the right of my acceptance region, this entire thing, because my null hypothesis is just that the probability of heads is less than 0.5, anything greater than 495 heads is my acceptance region, and all of this is your rejection region, and it forms this tail, right? That is a left tail test. It's pretty damned. Once you actually look at it, it's like, oh, the tail, the rejection region is to the left. Therefore, left tail test. Now let's say instead I take my alternate hypothesis is that the probability of heads is greater than 0.5. So what does that mean? Again, I'm assuming that the probability of heads is 0.5 when I'm plotting my distribution. But what I'm gonna say is that now, if I toss this coin 1,000 times and I get 500 and I get more, that means the probability is in fact greater than 0.5. The null hypothesis is false and I'm gonna reject it. If I get less than 505 heads, it means that the alternate hypothesis that the probability of heads is greater than 0.5 is false. My null hypothesis, the probability of heads is 0.5, is true, and I'm going to accept the null hypothesis. And this, as you might expect, gives you a right-tailed test, because the tail is to the right of the acceptance region. Now, two-tailed test. That comes if I take my alternate hypothesis as the probability of heads is not equal to 0.5. Because now what's happening? Right? Now, on average, out of 1,000 coin tosses, I expect 500. But if it's less than 495, so probability of heads is less than 0.5, means it could be greater than 0.5 or less than 0.5. Is not equal to 0.5 means it could be greater than or less than 0.5. So this is a combination of both. If I toss this coin 1,000 times and I get less than 495 successes, for now I've picked 495 arbitrarily, but it links with significance level. I'll get to that. If I toss this coin 1,000 times and I get less than 495 495 heads, then my alternate hypothesis is true. My null hypothesis, that this is a fair coin with probability 0.5, is false. But if I toss it 1,000 times and I get greater than 505 heads, then I am also going to assume that my null hypothesis is false and my alternate hypothesis is true. And now your acceptance region is here in the middle, around the mean 500, and you've got two tails off to the side, and that gives you a two-tailed test. So that's the tails defined. Now, I just arbitrarily picked 495 and 505, but you pick, there's an actually, so what will happen in a sum? You'll be given information by which to figure out what your null hypothesis is, what your alternate hypothesis is, and from that information, you will be given a significance level. From this, you will have to determine whether to reject or accept the null or the alternative hypothesis. So I already said the null hypothesis, the significance level, is the probability of reject the null given null is true. So what you need to do? Oh, and you'll be given a sample mean, probably. I'll elaborate from that later. And so what you need to do is, based on this sample mean in any question, and based on this other information, you need to define if you're accepting the null or the alternative hypothesis. Now, how you do that is based on this sample. How you decide if the sample mean is sufficiently far from the null hypothesis that you reject it is based on the significance level. So I'm gonna run through this practically. I'm literally inventing a sum for myself, right? What is it? So my null hypothesis, H log, fair coin. Okay, what that means is that probability of heads follows a normal distribution, follows uniform. Okay, see, here's the thing, I can't explain this. Okay, I kind of get why ma'am was simplifying it, because to go into the full complexity in this amount of time is not possible, but at the same time, to expect you to treat it at the superficial level is meaningless. Anyways, let me try my best. I'll try for 10 minutes more, and then I'll send this on the group. Whatever you've got, you've got. Maybe I confuse you more, maybe I help you out, we'll see. Right. You've got your significance level. Let's say I have a significance level of 0.05, right? What you need to do from your significance level is, so what does this mean? This means that I need to pick an acceptance region such that the probability, oh, by the way, acceptance region is just the range of values for which you accept the null hypothesis. So I need to pick an acceptance region such that there is only a 0.05% chance that you reject the null hypothesis when it is true. Now, how this pans out is going to depend on the specifics of the sum, and based on that, what your alternative hypothesis is. So I'm going to pick kind of the trickiest example just because then theoretically you'll understand the easier ones. So I'm continuing the coin toss example. My alternative hypothesis is that probability of heads is not equal to 0.5. Okay? I plot that because we're computing significance level. We're gonna assume that it is in fact 0.5. Now, my sample mean, my sample number of heads can be anywhere on this distribution, on a normal distribution. Okay? A singular coin toss follows a uniform 0.5 distribution, a uniform distribution. It's either 0 or it's 1, right? But my sample mean of the number of heads from an infinity number of coin tosses will follow a normal distribution. Because think about it. I toss this coin 1,000 times, I get 500 heads. Sample mean 0.5. I toss this coin 1,000 times, I get 499 heads. Sample mean 0.499. I toss this coin 1,000 times, I get 520 heads. Sample mean 0.52. Get my drift? Okay? And so, what's gonna happen? So n is the number of samples. So from that I get my sample mean. The probability that the sample mean is, the x bar will follow anything between 0 and 1, right? Because I divide number of heads, which is necessarily less than or equal to 1000 by 1000. The sample mean will be any value between 0 and 1, and it could be any of these, right? And so what you need to define with your acceptance region, when they have specified, and it takes these values with a probability. So the sample mean takes any value between 0 and 1 following a normal distribution where the mean is equal to 0.5 and the variance is equal to 0.25. Okay? So what you need to, so the sample mean will take any point, can take any point along this distribution, and over here and it can take it with varying probability. Alright? And when they say your significance level is 0.05, what does that mean? Let's say for significance level of 0.05, I define, let's say for a significance, there's a mathematical way to calculate this. I honestly don't really, I'd need to practice it a couple of times to explain it to you guys. And even then I'd need to figure out how to explain it. So I'm just not gonna bother. It's reasonably straightforward. But what we are saying is you need to find an acceptance region. So when your null hypothesis is that the actual distribution mean is not equal to 0.5, your acceptance region is defined as sample mean less 0.5 less than, we're going to call it delta, 0.5 greater than delta. So all I've written here is that my hypothesis is that my actual mean, the actual mean probability of a head is 0.5, and if I get a sample mean over 1,000 coin tosses between 0.5 minus something and 0.5 plus something, I'm gonna accept that hypothesis that the probability of a head is 0.5. Now, What is this something? That's where significance level comes in. And that's where this comes in. Because the sample mean follows a distribution. And what that means is that the sample mean takes values on that distribution with a probability. So the sample mean takes a value of 0.1 with a lower probability than it takes a value of 0.4. Because the distribution mean is 0.5. Right? And so what we need to define is this delta such that the probability that the sample mean lies between 0.5 minus delta and 0.5 plus delta is equal to 0.0, such that is equal to 0.95. Because think of what this is saying. What significance level is saying is that the sample mean will lie outside of our acceptance region 0.05%, 0.05 times proportion of the time, 5% of the time. And so what does that mean also? It means that the sample mean will lie within our region of accepting the null hypothesis 95% of the time. And so what you are doing is you are defining. So say I haven't done the math. I could actually do the math and I'd get an answer. So say I figure out there's a way to calculate this. I'll send my notes across because I honestly don't remember how to explain it. I don't remember it well enough to do it. I need to practice. But say I figure out that my acceptance region for 0.5, that my acceptance region is any value between 0.545 and 0.55. What that means, when I calculate my sample mean with 1,000 samples, 95% of the time, if the distribution mean is actually 0.5, it will lie in this region. And 5% of the time, it will lie outside this region. That's what that means. And so I realized that I haven't really explained to anything of like how to actually go about doing the calculations. I'll send my notes across for that, but hopefully what I have done is explain how to understand what the fuck you're doing when you're doing the calculation. So when I give you the formula, you'll be able to comprehend, okay, this is what's going on, right? There's probably more left to explain, but honestly, it has been over 40 minutes. I am tired. I have things to do. I can't be explaining everything as much as I want to. Maybe I just confused you all more. Maybe I confused you all, but I did better than Pallavi ma'am. Maybe she's right and I'm just a cynical asshole. Maybe she's gone way too far into simplifying things when nothing makes an ounce of sense, and I've gone way too far into giving you all of the nuance so that nothing makes an ounce of sense. Either way, hopefully something in that helps.